So another operation that we could perform with vectors is called the cross product. And the notation follows this. So A cross B is that. So one important thing is that the order does matter when performing the cross product. So what I'm saying is that B cross A does not equal A cross B. However, the magnitudes of the vectors that are produced from performing the cross product in either way actually do equal each other. So what I'm saying is that the magnitude of A cross B equals the magnitude of B cross A. That's what I'm saying. So now that we have those things in mind, orientation does matter. And we talked about this in the first video when we talked about the cross product of I and J. And it only points in one direction. So this actually points in the opposite direction if you're performing, J cross I. So that is the main thing that we're distinguishing here. So now I'm going to show you what it geometrically means when performing the cross product. So we're going to define our coordinate system in this fashion, a right-handed coordinate system. So this will be y, this will be x, and this will be k. And what I'm going to do, I'm going to define two vectors, a and b, and we're going to perform the cross product geometrically. So this is a, this is b. So what I'm going to do, I'm going to draw the cross product. So what we're doing, we're crossing a to b. So that means our thumb would be pointing in the upward direction. So here we go. So this is A cross B. And what's important about A cross B is that it's perpendicular to both B and A simultaneously. So it points, in this case, it points in the positive K direction. So that is what the vector is. And the magnitude of the vector, A cross B, is actually equal to the area of the parallelogram that is made by the two vectors that are being crossed. So A cross B is the magnitude of this area. So that is a very important geometric property that you probably see in multivariable calculus mostly, but that is important to know regardless. So here we go. Now I'm going to show you why B cross A is not the same thing. So we're going to have the same coordinate system, and then we're going to draw the cross product. So this will be x, this will be y, and this will be z. So now we're going to define B cross A. So we have the same vectors pointing in the same directions, or almost in the same directions, and then this is B. So now what we're doing is that we're crossing B and A, B to A. So we're doing this direction. So that's B cross A. If we perform that operation, we'll get a vector pointing actually downward. So now this will be B cross A. However, the magnitude created by this vector is actually equal to the area of the parallelogram of these two vectors. So this will be B cross A. And these two equal each other as stated before. So that is the geometric meaning behind the cross product, and it can be used extensively, especially in calculus. That is not useful, as many things are not useful when using geometric solutions, because the geometry becomes difficult when arbitrary vectors lie in arbitrary 3D space, so you can't really perform the geometry quite nicely onto paper or onto a graphic tablet. So we're going to define the cross product as we did with the vectors before in an algebraic sense. So A cross B is going to equal a 3×3 determinant. So if you don't know what that is, I'm going to show you how to solve it, and it's pretty simple how to set it up. So what we're going to do, A cross B is I, so we start with the first row with the components of your orientations or your axes. So in our case, X, Y, and K. So this will be I, J, then K, and then we're going to close off that. So in the first row, you put it the vector that starts the cross product. So A will go in the next row. So AX, A y a z. And now you put b in the final row. So it'll be b x, b y, b z. And now we're going to perform the cross product. So I wrote out the 3x3 determinant 3 times. You don't have to when solving this. This is just for me, for you to understand this more clearly, because what I'm going to do is I'm going to make it a little bit messy. So each I'm going to go through, there's 3 steps. I'm going to go through each step onto these 3 different determinants. So what I'm going to do is do the first step. So the first step, what you do, you cover up the I column. And the I column represents the I position of the vector A cross B. So what we're going to do, we're going to cover up the I column, so we're going to ignore it, and keep in mind that this is the I component. And then we're going to do the 2x2 determinant of these bottom 4 components of A and B. So what you do, you multiply across here in this direction, and then you subtract the multiplication in this direction. So step 1, so this is step 1, we're going to do AY times BZ minus AZ BY, and this whole thing is multiplied by the I component of the vector A cross B. So that's step 1. Now we're simply going to repeat this process, but for the next column. But this column is special because we got to include a negative sign for the J component, and you'll see what I mean by that. So we're going to cover up the J component, or the J column, and now we're going to perform the 2x2 determinant of the remaining components of the vectors. So this will be AX times BZ minus AZ times BX. So this is step 2. We're going to do this. Okay. So we got to include that negative sign. Whenever it's the J component, always include the negative sign. I remember I couldn't solve problems in dynamics because I didn't understand, or I didn't understand. I'm saying I forgot the negative when I performed the cross product, and that missed a lot of problems as well as on some exams. So that's very unfortunate. So don't forget this negative. It can be very crucial when you solve problems. So AX times BZ minus AZ times BX, and that'll be the J component. So don't forget the negative for the J component. I cannot stress that enough. Alright, and then we're going to do the last step, which is basically the same thing. So we're going to cover up the K column and then perform the 2x2 determinant on these. So this is step 3. So then this will be AX BY minus AY BX. This whole thing is multiplied by the K component. And once you do all these steps, you simply add these things together and you'll get a vector that points in this direction, or whatever direction that are perpendicular to A and B. So here we go. We're gonna, I don't want to, okay, so sorry about this if it's out of screen a little bit. A cross B equals AY BZ minus AZ BY I minus AX BZ minus AZ BX J plus AX BY minus AY BX K. So this just comes with a habit and, you know, just doing a lot of problems, and you'll get this down. And just, again, please don't forget the negative sign. That was a horrible thing to happen to you. But yeah, that is the algebraic way to solve cross products. So now you don't have to worry about the geometry, like where do the vectors lie in space, and how do I find the normal component of those two vectors simultaneously, all those different things. But now you can solve in an algebraic sense, so it's just straight multiplication and addition and subtraction. So that's it for the cross. Oh, one thing before I end this video, you might be wondering why the cross product might be useful. The cross product is actually a definition, not a definition, a technique used to define the idea of moments and torque. So when we get to rigid bodies and ideas of equilibrium, we'll see that the cross product is very useful when solving statics problems. So we'll be using that in the future, and that is why the cross product is important, at least in statics.